In section 4.5, we're going to talk about locating zeros of a polynomial function. We've actually already talked about utilizing the graphing calculator to help us find zeros of a polynomial, which is great if the answers are rational. But what if the answers are irrational? And we want to find the decimal values at which a zero occurs. Well, we're going to utilize our graphing calculator again. I want to start by looking at the function f of x equals x squared minus 4x minus 2, and I want to determine between which consecutive integers the real zeros of the function are located. So using the graph, I can see that one of the zeros is clearly between 0 and -1. And I shouldn't write that like an ordered pair. Let's write it like this. One of them is between 0 and -1. And then the one over here looks like it's between 4 and 5. But what if I want to find their exact locations? Remember, they're not necessarily rational numbers. They could be irrational numbers, those non-repeating, non-terminating decimals. There is a zero function on the calculator, but there's an easier way of determining the zeros. So what I'm going to do is in the y equals function, in y1 equals, I'm going to put the function that I want to find its zeros. And in y2 equals, I'm going to put in 0. What that's going to do is it's actually going to think you're also graphing the x-axis. So then when I go back to my graph, we're going to use the intersect function in order to find the zeros. So now what we're going to do is back on our graph, if you go to second trace, that doesn't look very nice. Let's try a different color. If you use second trace, and then you go to option number 5, which is the intersect function, and your cursor will pop up right here. You can actually just leave it there and hit enter 3 times, and it's going to tell you that that zero that's between 0 and -1 is approximately -0.45. To find this zero, on the right-hand side, you'll need to go back to second trace 5 again. But this time you're going to need to move the cursor closer to that 0, or right on top of it, whichever you want to do. Then hit 0 3 times, or enter 3 times. And it will tell you that that 0 is at approximately 4.45. So we know that with a quadratic equation, the most amount of times it can hit the x-axis is twice anyway. So we knew there'd be 2 solutions, and we used the intersect function to find them, but we needed to put 0 into y2 equals so that we could do that. You can use the zero function too, but it's much easier to use the intersect function. Let's do this one more time. Let's look at the function y equals x cubed minus 3x squared minus 2x plus 4. This is what the graph looks like. Now, the problem we're going to run into is it looks like it's at -1, +1, and 3. But if you go to the table, you're going to see that only one of the zeros is at an integer. The only one that's actually at an integer is 1. The other ones, I want you to look at the y values here. You see how between -2 and -1 the y values switched between negative and positive? That means the graph must have crossed the x-axis. So let's go back and look at this graph again. One of the points was at -2, -12, which was down here somewhere, and then the next one was at what, -1, 2, which is up here. So in order to get from here to here, it had to cross the x-axis. So the easiest way to check a table to see where a zero might be occurring is looking for a change in sign of the y value. I also want you to notice down here from 3 to 4, the y value switches from negative to positive. That means it's crossed the x-axis. So one of the zeros is between -1 and -2. One of them's actually at 1, and then the other one's between -2 and 12. Now let's actually go find those zeros. So on our graph, we're going to call up the intersect function, so second trace 5. Why don't you start by getting your cursor as close to that 0 as possible, and then hit enter 3 times. It's going to tell me that it actually occurs at negative 1.24. This 0 we already know is at 1. But now let's go find this one. So second trace 5, move the cursor as close to that 0 as possible, and then hit enter 3 times, and it tells you it's approximately 3.24. So that's how we find and approximate the real zeros of a polynomial. So in this section, it is okay to give me decimal answers for all the polynomials, rounded to the nearest hundredth.